Hello, here we are today discussing the lead paste distribution aid for my senior project. A bit of an introduction on what I'll be doing is when a battery company wants to test new materials inside of their battery, they have two options. They can test the new materials inside of a standard battery and kind of slow down production, or they can use small scale cells to test the materials. So for this, we're going to be focusing on the small scale cells. These are often hand pasted and can take weeks or even months to create. The hand pasting is the largest holdup in the process and the most damaging to the paster. The paster is unable to stay in neutral postures while working, meaning that for hours at a time they're in an awkward pose that can damage their body. This presentation will be discussing the creation of the small-scale pasting machine, and I want it to be used and shared and be able to be modified between different battery companies. The majority of this machine is going to be 3D printed on ABS material to cut costs. It also maintains corrosion resistance and also keep this design as highly modifiable as possible. A bit of background on where I got all the ideas from to create this machine. So the overall design is based off the current process of the hand paster at the Hammond Group. Balls of paste are pre-weighed to about 1% over the desired wet weight, and then there's one ball of paste per one grid. Grids are laid flat over a damp tissue so that the paste is only going to be sticking to the grid and not anything else underneath it. The paste is applied, and then a small scraper about 2 inches by 3 inches is used at a 30-degree angle to smooth the paste into the grid, filling all the holes. From there, the grid's flipped over, paste is applied to the backside in the same manner, and then they're put on a stack and into the oven. But pretty much when looking to create the pasting machine, you want to look at an already created machine. All of them have three basic components. There is the orifice plate, the belt, and the supporting structure. The orifice plate is there to let the paste come from the hopper onto the grid. The supporting structure holds the grid on the belt while it's moving through the machine, and then it can also, depending on the machine, can let paste go underneath it as well, and then the belt is physically moving the grid through the machine. One thing about pasting machines is if you ever want to change or add new materials, you change the density of the paste, you're going to have to tear apart the machine and then replace components with new components, so it'll work. When you're changing stuff like that often, you're going to have either multiple pasting machines or someone that can continuously tear apart the same pasting machine. For the small scale one I plan to create, there's not going to be an actual orifice, but there is going to be a blade and a hand-operated rack and pinion. So the rack and pinion is going to be transferring the grids from one side to the other. But instead of a belt, which is mostly used for high volume, the rack and pinion can do just fine for the couple hundred that we need to do on the day. And then the supporting structure would be like the volumetric mold and the blade. And that's kind of the supporting structure and the orifice plate all in one. So for trying to maintain the same weight of paste for every grid, the height of the blade would be adjustable to the size of the volumetric mold and how much paste we want on there. There were a few resources that were used to aid this project. Pasting machines aren't typically written about or discussed, but their basic concepts and theories are. So one of the biggest things I was able to look at was like the Wirtz patent. They've even invited me to their facility to come look at some of their machines and check out like what they have inside of their hoppers, just because they know I'm not technically competition, but I'm just trying to help my job. Others are kind of like this book right here. They talk about the different rollers and the forces that are used and kind of different shapes for rollers, knurled rollers, their strengths, their weaknesses, and how you can use them. Another one talks about the materials that are actually going inside of the paste and the rheology of the paste and the density and how it'll be affecting just how it dries and how much dust could be created or how it'll move. So that'll be important to know because I want to know what's going inside of my machine. It also discussed an interesting topic about acid spray. After the plates are pasted, there's acid spray going onto them, and that kind of improves the plate quality, and then it also reduces the dusting, so there would be less lead in the air. Another book kind of discusses the grids and what grids can better accept paste on them. Kind of like the rougher grids are easier to paste because it wants to fill those cavities, versus the grids we currently use at the Hammond Group, which are punched, and so they're very smooth and it's harder to get the paste to fall into the holes. A couple other resources I used were these two. So for the developments in paste mixing for lead acid batteries, it talks about the actual pasting machine and what kind of materials are used for their tubes or for their hoppers, and then how easy it is to take it apart and use it, and then kind of different rollers, and all of this stuff is stuff that I plan on using as well. And then finally I looked at cement pastes. Cement is remarkably similar to paste, kind of in how it's made. There are fibers and reinforcing agents that are needed, and when trying to mold it into a certain shape, it works really well, or they follow the same characteristics. Some of the calculations I used, or the main calculation that I have to use, is for the volumetric mold. The density and the mass of the paste are predetermined, and then they'll be entered into the first equation. From there, we can adjust the height of the blade because we already know the length and the width, and everything else that'll be following in. As well, there's going to be the force for the rack and pinion. To push the paste through the grid, the rack and the pinion are going to be running under that blade, so we kind of want to know how much force it's going to be used to be going in there. And then as well, we'd like to monitor the acceleration because we have to know how fast we're going to be going. If you go too slow or too fast, it could leave spots in the grid. And then there's also calculations for torque on the pinion, so how hard is someone going to have to turn that handle? Are they going to get tired from that? Will we eventually have to add like a motor or something else to kind of make it easier on people, depending on how many we're going to have to do per day? And then this is also, like how I was talking about the acceleration, this is the rotational speed of the pinion, so it's pretty close. If we're going too slow, it can cause the paste to collect near the blade, and then it will bind up, and then it will destroy the grid. Too fast, paste might not enter the grid at all. Some goals for this project are just the basic goals. Creating a pasting machine for the miniature battery cell grids. It has to be able to have repeatable results with proper paste adhesion. It has to be corrosion resistance. Iron will kill a battery. It has to be safe to use. We don't want anyone getting hurt. So that would be like the lead dust per OSHA standards. And then we have a smaller hood that is rated for lead dust, so it would be preferred if it could fit in there, or have a vent that could fit in there. And that has to be easy to understand. I know I would understand it, but when I give it to someone else, I want to make sure that they are also able to understand it. Some specifications for this project are the blade cannot move at all. The blade and the rollers cannot move at all. If they're moving, then that means that different amounts of paste are going to be on the grid, and that's not something we want. It has to be 100% corrosion resistance. Because of the constant exposure to acid, the steels do tend to oxidize quite quickly, and then once that iron gets into the plate or on any battery plate, the battery is pretty much worthless, or the plate is pretty much worthless. We want the airborne lead particles to be lower. This is the OSHA standard, lower than the OSHA standard. And then the actual height for the blade, we want it to be adjustable so that we can change it, because one of the main things we do is test the materials inside the batteries. So always testing this, it's always going to be changing everything. We want to try and get one plate per 45 seconds. That would be about twice as fast as the current process, and even if it was a little bit longer, that would still be faster than where we're at now. And then current goals are roughly 10 grams of wet paste per grid. Some of the deliverables for this project is the design package, and that includes the pasting machine. All of the parts will be available. They're going to be low cost through 3D printed. And then we're going to offer this to other R&D groups, any other battery companies that would like to use this machine or the design. They'd be able to take it and modify it from there if needed. We're pretty much removing the hand pasting process. That's going to be something that'll give a drastic change, extra time from the workers and everything. There's going to be a risk analysis performed and delivered when the machine is fully created and functioning, and then the analysis and test data. So anything we see from the rollers and how everything is working, how the plates are coming out, how fast are they coming out, everything there would be in its own separate little packet. So here are some of the current designs for the battery pasting machine that's already been created. This is the first initial prototype. It was pretty much less than $30. We have the 3D printed rack and pinion, all the separate gears, the handle that was donated from another project, the chisel, and then everything was just made from scrap wood. So we would like to create a second one that is just a little bit nicer quality. This one has a lot of bad tolerancing, it has a lot of flexing, it does not move very well. And then we'd also like to add new components. So these are different rollers that could be used in the design, and then we have the volumetric mold that'll be moving through, and you can kind of see how it'll be holding the grid there. The actual design was created on SolidWorks, and then from there more components can actually be added to kind of see how it'll look or how it'll feel before rebuilding a whole new one off of the top of my head. And then we also have the inside view where you can see that the blade, the volumetric mold's right here, so it'll be moving under the blade. The blade is stationary, it's fixed, and it'll just scrape the paste right into there. For what's already created, I did create a risk analysis, which is pretty much just to determine the risk level that each hazard has, and it's based off the probability and the impact. And also there are some control measures used. Two of the main hazards are lead dust, which has the total risk level of 20 because the probability is quite high. We do work with lead every day. We are literally holding lead in our hands, so we are very likely to encounter it. But the impact is also high because you can get serious side effects from being around lead too much. Our lead blood levels are monitored, so while using it, if someone's using it more than another person, we'll be able to see that lead blood level rise. To kind of try and curb this though, we could direct any excess lead dust into that vent like I said earlier. And then another hazard would be breaking of the 3D printed components. It's not as dire, but it would make it a rougher time if the machine were to break while using it, because not all parts are duplicated or recreated, so we'd have to wait for the printing time, and then we're just wasting ABS material at that point because we have to try and figure out why it broke. For the budget, at maximum, pretty much 1/2 of a roll was used to create what you already saw. So that's where I kind of estimated the rest of how much more MakerBot filament we would use. Everything from there, we have the nicer wood that we plan on using, the chisel that was used, the conduit for my shafts, and then the handle that was donated. And eventually I want to do those safety guards for the plexiglass, so I did add those in there now because I know that's something that I do want to add. What wasn't on there was the labor hours. My labor hours are kind of estimated at 5 hours per week during the 2020 semester, the 16 weeks of the 2020 semester. It doesn't include any additional time spent outside of the facility. And then we also have the schedule. So I kind of tried to break it up and make it a little bit easier to see some of the milestones. A total of 48 weeks are planned in this project, and they're broken up into 5 periods. So here are the periods, here are their milestones. So for like period 1, we were able to study the basic design and then print any necessary components, which is pretty much what I already created. From there, we're still currently in period 1. We're going to be moving to period 2 pretty soon, in about a couple months. From there, we're going to test the machine, kind of see how it's working, start gathering that test data, test and study the rollers, study and verify any speeds and the quality of the pasted plates. Period 3 is having the prototype, the new lower tolerance prototype design complete, and then designing out any parts that are corrosion resistant, so like the conduit shafts, we should probably get those out of there, stuff like that. Have the final budget with all of the final parts ordered, any final calculations have to be done in period 4, and then we're going to be completing the drawings and the parts list. And then period 5 is pretty much assemble. We're going to be calling it the prototype 2 with all of the new parts, and then just verifying that it's still working just like we wanted. Here's the Gantt chart of the schedule to kind of show how it's broken up. A lot of overlapping is there, but I tried to break it up just to make it easier on myself to understand what needs to get done and when. And then finally we have the QFD chart, which is to make it easier for the, it links the engineering specifications to the customer requirements. So it lets the engineer know what is the most important of this machine. I shouldn't be spending all my time on one part when another part's more important. So like for this, the most important, which is the highest number, would be the volumetric mold. And that's just because so many other things rely on that it has to be done well. While the lowest would be the vent directed to the hood. We're all continuously exposed to lead, and we also have respirators that we're supposed to wear, so that's not as big a requirement or a big as worry as the mold is. That's something that has to be used continuously over and over and always work every time. So that was my presentation on my report. Thank you.